Hey everyone, welcome back. Let us see some more examples to analyze time complexity. The first example for this video is I start from 0. The condition is changed, gets incremented by 1 for every iteration, and we'll be having some statements inside for loop. And we'll end the for loop. Let us dry run this. We'll have I update statement and the statements inside for loop. For this dry run, we'll consider n as 10. I is starting from 0. The statements inside for loop gets executed one time. Now the update statement is triggered, which gets updated to 1. Now I is 1. Now the condition check 1 into 1 less than 10, which is true. The statements inside for loop gets executed and I gets incremented to 2. Now I is 2. The condition check 2 into 2 is less than 10. 2 into 2 is 4. 4 is less than 10, which is true. For loop statements gets executed one time. I gets incremented to 3. Now I is 3. Condition check 3 into 3 is less than 10, which is true. Statements executed one time. I gets incremented to 4. I is now 4. Condition check 4 into 4 is less than 10, which is false. So the for loop breaks here. For loop is breaking since we know the value of n. But what if we don't know the value of n? Until when our for loop runs? To find out that, can we just identify the pattern over here? We have 1 into 1, 2 into 2, 3 into 3, 4 into 4. Can't I just write this as 1 square, 2 square, 3 square, 4 square? All the values holds good. Now our for loop runs until something square is less than n. Isn't this correct? And can't we consider this something as k, which is unknown for now? For loop runs until k square is less than n. We need to find this k. To find that, we need to check when our for loop ends. Our for loop is ending when I into I is greater than n. I into I is greater than n. This can be written as I square is greater than n. This will give lead to find k. For loop stops when I square is greater than n, and we know what is I, which is nothing but k. We can substitute that up here. I square is greater than n, k square is greater than n. We are just substituting the value. To get rid of this exponent, we can apply square root on both the side. Root of k square is greater than root n. This gets cancelled. k is greater than root n. Finally, we got the value of k. Therefore, our for loop runs until the value of I is lesser than k. So the time complexity of our above for loop is big O of root n. I hope this thing is clear. Now let us see our next example. And the time complexity of these for loops we have already seen. We'll just see the order now. I plus plus and some statements. One more for loop. Pause this video. Try to get the time complexity of these two for loops. I hope you got the answer. Let us try to see it. We know this for loop gets executed n times and below for loop gets executed n times. Now you need to answer, will the time complexity be n square or 2n? Since these two for loops are separate, we will be adding n and n, which is nothing but 2n. And we have already discussed, we will be ignoring this constant. Therefore, the time complexity of above function is big O of n. The next example is for int I equals 0, I is less than n, I equals I into 2, and p gets updated. We'll have p over here. For j equals 0, j is less than p, j equals j into 2, and some statements inside this for loop will end the for loop. We have already seen these kind of for loops. Let us try to find the time complexity of these things. The time complexity of first for loop is log n. Since our second for loop is running until it is less than p, we can consider p as log n because p is getting incremented as many times as our first for loop is running. So we can consider this log n as p, and our second for loop runs until j is less than log n. Since our j loop is getting incremented by the multiples of 2, the time complexity of this loop will be having a log in it, log of something. This something is nothing but p because our for loop runs until j is less than p and stops when j is greater than p. So what we can do is, we can consider the time complexity of this j loop as log p. We know the value of p is nothing but log n. This becomes log of log n. After adding these two terms, we'll end up with the time complexity of these two for loop. Log n plus log of log n. We have already discussed, in terms of time complexity, we will be always considering the dominating term, which is the dominating term here, log n. Therefore, the time complexity of above two for loops is nothing but big O of log n. I hope you have understood this example. We'll move on to our next example. For I is 0 goes till less than n, gets incremented by 1 for every iteration. And inner for loop starts from 1, goes till n, and gets incremented by multiple of 2 for every iteration. And we will be having some statements inside inner for loop. We know the first outer for loop will take n time, and we also know whatever that is inside outer for loop will also run n time. So this runs n time, and the statements inside inner for loop will also run n time. But we have inner for loop as well, right? This for loop runs log n time because we are updating the value of j with a multiple of 2. After doing all the mathematics operation, we will be getting the value of k as log n, which gets multiplied with outer for loop times. And the statements inside inner for loop will also take log n time, meaning will also execute log n times. After adding all these terms, we'll end up with the time complexity of this for loop. N log n plus n log n, which will be n plus 2n log n. The dominating term is 2n log n. We'll ignore the constant 2, and we will be considering only the n log n as time complexity. And you should not be having a doubt why we are ignoring n and 2 by this time. Therefore, the time complexity of above for loops is nothing but big O of n log n. That's it for this video. Let's summarize all the 3 videos of our time complexity examples. We have seen a for loop of this type. I starts from 0, I goes till n, gets incremented by 1 for every iteration, and the time complexity of this kind of for loop is nothing but big O of n. And the second type of for loop is for I is 0, I is less than n, and I gets incremented by 2 every time. This can be written as this: I equals I plus 2, and the time complexity of this for loop is nothing but n by 2 after considering the degree, which will be order of n, big O of n. The third type of for loop we have seen is I starts from n, goes till 1, gets decremented by 1 every iteration, and the time complexity is same as the incrementing for loop. The fourth type of for loop we have seen is which starts from 1, goes till n, but gets updated with multiple of 2 every iteration, and the time complexity of this is nothing but big O of log n. The fifth type of for loop is for I starts from 1, goes till n, and gets incremented with multiples of 3. Even the time complexity of this is log n. This will be log base 2n, this will be log base 3n. But the constants are ignored. We will be taking big O of log n for both the for loops. The sixth type of for loop is for I equals n, goes till 1, and gets updated by 2 every time. The time complexity of this is nothing but again log base 2n. which is nothing but log n. The key points you need to remember here is this for loop will be considered as 2 power k, and after finding the value of k, we will be getting O of log n. And this for loop will be having 3 to the power k. This for loop will be having n by 2 to the power k. To know how these values are derived, if you have not watched my previous videos, please do watch it. You will clearly understand. I hope so far all the 3 or 4 videos are helpful to you in order to analyze the time complexity of any loops. In the next upcoming video, we'll be analyzing the time complexity of while loop. Thank you all for watching. See you in the next one.